Good morning, everyone. Hear me? Oops, there's a bit of feedback. Okay, now it should be fine. Okay, let's get started. This will be the final leg of the 14-week lectures into artificial intelligence. So let's continue with the last topic. This is introduction to support vector machines. So for the rest of today, we will see how we can use the support vector machines and what are the key issues of your support vector machines. Now, oops, sorry. It doesn't work. Oh, before I forget, any questions from the previous lecture or comments? No, it doesn't work. Got to speed it up. Okay. So we talk about the support vector machines, and then what is the learning outcome for this particular topic. I think we started with the history and the motivation of the support vector machines. We look at some of the fundamentals or foundations related to support vector machines, some of the mathematics behind it. We talk about similarity measure, right? Dot product. We also then look at what we mean by the feature space and kernels. I think that's where we stopped from last week. Okay, so we just only barely scratch the surface of support vector machines. Let's continue. Okay, I think I've updated the notes for this since last lecture this Wednesday. I updated the notes on the kernels. I think the earlier one was a bit maybe not so clear. So actually, I expanded and include a few more points on these kernels. So basically, we mentioned that kernels are to map your initial, say for example, your kernel, or rather your initial feature space, right, consists of x1, x2. Now we want to map it to a new feature space under R. So this is basically your kernel function. Now, the other thing you must consider is that kernel must be equivalent to an inner product in some feature space. So basically what it's trying to say is that you must maintain the relationship between, say, x1, x2 in the original space, in the new space, right? So it makes sense. If you look at it closely, it makes sense because we do not want to change too much, right? We just want to change the what you call it, overall. The maybe will become clearer in the next few slides. So basically, if how is x1 related to x2? That particular relationship must also be maintained in your new feature space. So this is what it means by you must also maintain the inner product in your new feature space. As I also mentioned, what are kernels? Kernels basically, if you look at the convolutional neural net, we actually talk about this a little bit. Maybe not. One of the main things in a convolutional neural net is that we use a lot of kernels to actually convolute your input data into the feature space. So this is in the CNN, right? We talk about the kernel as a form of filter, right? That is used to extract the features from images. So this is basically another look at what is a kernel. Maybe simpler. Now, other than the three examples of kernels that I showed you in the last lecture, We also talk about here. I'm giving you more. So I think some of this will be familiar to some of you because we have this linear. We talk about this linear, and then now we have this sigmoid polynomial and the k-mod RBF radial basis function. Basically, it is you can see here, and then of course exponential RBF. So this one doesn't square. It's the only difference. Of course, as I said before, there will be many more up to the scientist, engineer, or developer who actually tried out various types of kernels. Now, why do we want to dabble? Why do we want to use such kernels to become clearer when I show in the next few slides? So kernels are widely used in support vector machines to bridge the linearity and the non-linearity, right? So it converts to a non-linear lower dimension space. Right? Initially, your data, they are actually the points, the piece of data, are non-linearly related in such lower dimension. Now we want to map it to a higher dimension, whereby we can then get a linear classification. You look at it closely, what does it mean? It means that in the lower dimension, the data is actually non-linear. Right? Now, when we map it to a higher dimension, in a higher dimension space, whereby we still maintain the relationship between your data. We maintain them and we transform to a higher dimension. Now, this higher dimension, what is the requirement? When you transform to a higher dimension, basically the transformation will convert that from non-linear to linear in that linear space. So therefore, with such a linear space, I can then use my support vector machines to classify the points, the data that we have. Okay, so these are some of the visualization of your various kernels. You can see here the sigmoid, the Gaussian kernel, RBF, radial basis function, your polynomial. Of course, we still have your standard common. This is the simplest of all the kernels that we have, which we will talk about this in the rest of today, in today's lectures. Any questions, comments so far? And follow? Okay. Let's now, I think that was basically where we stopped at the previous lecture. So let us continue now and look at this particular topic. So if you look at the title here, we are trying with the two terms, clustering and classification. They can be quite confusing for some of us, right? So basically, what is clustering and what is classification? So on the left-hand side here, you can see that one of the definition, right, of what do we mean by clustering is that a method to identify a set or a group of similar items. So this is basically your clustering. Now, on the other hand, if you look at classification, basically classification, we are trying to learn a pattern that maps an item into one of a set of predefined classes. We are trying to learn how the pattern can be mapped into one of the set of predefined classes. For example, if I look at my edible bird's nest, right? I'm trying to learn for this particular sample that I have, which of the grades, which of the classes it can go into, right? This one, does it go into grade AA? Does it go into grade A, or does it go into grade B? So that is the process for me to teach the artificial system to learn. Where does this go to? So this is called classification. So what do you see here? What else do you see here? You see that basically this one needs a teacher. They'll tell you this one goes here, this one goes here. This one, there's no teacher. You organize it as you wish, as you see fit. So this one is unsupervised. This is supervised learning. So again, let's look at the example. How do we identify apples and oranges? Left-hand side is a beautiful Washington red apple. Right-hand side is an orange. So these are actually good examples because they are about the same size and they are quite easy to actually explain. Okay, so when we have data, we want to fit, the data will fit into we call it clustering, fit into the groups that we see they actually belong to. So this is your clustering. This is at the end of the day, when you actually use the method here, put the metadata, and you actually extract the features, and then you actually organize them into groups or clusters. That's why the word comes in clustering. So if you perform further clustering over here, it will reveal that only very strong signals aim at finding positive acidic classes or clusters in the data. So you have to figure out, not you as in person, you as in the method, the algorithm have to figure out which one has a stronger signals, and as a result, these stronger signals means that they belong to this particular cluster. Okay, so again, now we have this. Right, so this is your plus. Right. Okay, so we have your clustering. Printing your data, and then you actually say that this group here, this is a method. Then you teach the algorithm, the method, or the technique. Let's say this samples here are apples, and these samples here are oranges. So that is involves extra knowledge learning step. So you learn that these features, right, belong to apples, and these features belong to oranges. And then you have your classified data correctly. So this is a apple, and these are your oranges. So basically, you have to perform a training step to train your. After training it, you train it, and then your new data that comes in, then will fit into any of these. It's close enough, similar enough to the two clusters in this example. Now let's look at the more examples of your clusters. What do you mean by clustering, and what do you mean by classification? So here you can see, right? I have data. I have my samples of points. Samples of points shown here. So basically, as I said before, this will be features extracted from some objects or some problem that we're trying to solve. So here, what can you see? So if you were to extract the data well, right? Extract the data well, you will see this. Right? You hope to see that anyway. You hope to see this. You can see logically, this one shows that indicates that there are three natural clusters formed. One here, one here, one here. That's what we believe, right? So again, we're right, because we then use the method to actually classify or cluster the data. So you can see here, this one belongs to the red classes, this one belongs to the blue classes, and this one belongs to the yellow classes. Now, how about this? This is actually from the IRIS, well-known, well-studied IRIS dataset. I think maybe later on we'll talk a little bit about this, the IRIS dataset. Right? IRIS is a flower. So we're trying to see that now. What do we see here? So if you were to extract the features of your iris flowers, there are actually three types of iris flowers in this example. But we can clearly see, probably see about two, right? We can't see the third class. Here, I think we can sense that this one is quite nicely clustered. Right? They are actually quite tightly clustered. They seem to be tightly bundled together. And this one, it seems that there is two classes because it's quite a big area compared to this one. Not so tight. Let's see what happens. I can see there are. So if you were to apply maybe a classification method, you find that these points here, okay, consists of actually two classes. You have your yellow and the blue classes. In a way, still quite nicely separated, but again, not as nice as before. Right, not as nice as before. But using maybe a powerful method, a powerful technique, a powerful algorithm, you can actually separate out these two classes here. Now, this is another sample, another data set consisting of broken classes. This is actually broken classes, and see here, this one actually, if you were to just look at this visually, if you extract the features into these two dimensions, you can see that it's not easy to separate. I will not know how many classes this one is. Right? Actually, there are many classes. I can see 1, 2, 3, 4, 5, and 6 classes, and it's not very apparent. Right, so this is one of the challenges of classification. We are trying to separate them. So you can see it's not, you cannot linearly separate them. Linearly means that not easy. You cannot draw a line across any of these data to linearly separate them. So that is the challenge of this non-linear data, or rather non-linear data in the lower dimensions. Right. So why do we want to study? Why do we want to develop classifiers? Right. So here we know that these are some of the common reasons why. Let's look at them one by one. The first one is actually it will help you to facilitate efficient search for information. If you can classify where the information is, classify into the correct groups, correct bins, right? You can also improve content filtering, for example, spamming, to separate your spam from your good emails, right, from your friends and those from spamming, right, or pornography. This will be quite useful for the government or for law and what called enforcement agencies to look at that. And also, classification is needed when you have different types of data or unknown values. You want to separate them into the correct classes. This one here on the left-hand side, the bottom one here is recommended system, right? So I think if I might share with you, if you go shopping, especially in those what do you call it? I'm not sure whether this Shopee actually does that, but I know that in this Amazon, it used to be a book company, but now they actually expanded into many areas, diversified. You find that if you go there, visit their website long enough, a few times, and then your data will be collected. They will look at what are the things you're interested to actually click and then see further, right? So you can find that after a while, they will then send you, they will recommend to you, you should also look at these things. So this is your recommended system based on the way you actually surf in that area. Okay, so I thought here's some music. Then there is also unstructured large amounts of text documents. So that really is useful for you to organize. If you have a large amounts of data, how can you organize them? And this would be very useful actually to look at your, for example, for spending patterns. So this will be useful for even if we do not go for online shopping. Now, nowadays, there are many companies, many supermarkets, they have these loyalty cards. Loyalty cards, especially if you use them, right? If you use them to buy things, to get some points, right? After maybe you pay by cash, you want to collect points. So you show the cashier your loyalty card. Now, once you have shown a loyalty card, I know what you are buying, what you like to buy in this shop or in my shop. Over time, I know that what is your spending pattern, what interests you, right? So as a result, I can then later on email you things relevant. For example, I know that you like to buy, for example, milk powder. You like to make milk powder and you like to buy, for example, baby food, for example. Then later on, I find that, hey, I know that you like to buy milk powder and baby food. Now, next time, if my shop start to sell baby napkins, for them to wear, I can then send to you, recommend to you, hey, you should also look at this because I sense that, because I know that people who actually buy milk powder and baby food, not you, maybe not you, other people, right? They also buy baby napkins. So what does it mean? That means you belong to that group of people that actually have babies in the family. So as a result, I can then send you that. If once I send you, that interests you, and you can also shop more from my shop. So this is one of the reasons why classification is actually useful in either the conventional shopping or even in e-commerce. So these are the other uses of your classification. So we have here, you can classification of classifiers and group documents into different domains. It's useful for domain-specific information extraction. That's why I said this is the one I talked about just now. It learns or reading interest of users. It learns your what you like to read, especially go online. It can help you to sort emails into spam or non-spam. It can be used in online new event detection. It can be used in knowledge management. It can be used in decision support in your CRMs and also personalization. How do I personalize your profile? So that, as I said, I can then send you things which probably would interest you. Now, that was the motivation why you want to look at classification. I think so far we have studied a few methods so far in this 13 weeks of lectures. We talk about the neural networks. We also talk about Bayesian decision theory, and those two actually can also be used to help you to classify your data points. Now, the rest of this actually, except the last one that Fuzzy said, the rest of this actually are some of the few examples. I'm not saying it's a complete set, it's just a few examples. As you know, I think there are many out there actually that use, of course. So one of them actually is very simple and yet very quite effective, which is your K nearest neighbor classifier. You define K from a user's point of view. You define how many nearest neighbor you want to look at. Right? So K is actually specified by the user, and then from there, the method the classifier will then will arrange for you the data points that you have. Genetic algorithms, we touched a little bit about this, especially in your second. I think the lab number 2, the module number 2, we talk about the search using the simple search, your random search, and then also your nearest neighbor search. We also show to you the example of how more powerful search can be genetic algorithm. Case-based reasoning, which is CBR. This is actually more of a expert system type, rough set approaches, fuzzy set approaches. Also, I think I've shown before the ACO, the N-based N colony optimization can also be used for classification when you organize your data. I think also we touched on a little bit of this in the tutorial of swarm intelligence, especially on the N-based N colony optimization, right? We studied that and we studied this. Now, with so many methods out there to classify your data, right? So which one are better? None are best, so to speak. You can't say this one is the best because it will depend on different problem set itself. So different domains will produce different performance on any of these methods. And so again, that's why we actually suggested as part of the process for you to do a successful final year project is to do some literature review to see what are the methods people have used before, and then from them maybe use like the same method that other people have used, and then they find that the method works quite well. Okay. Now let's look at the perceptron again as a linear separator. Remember we talked about this before when we know that the perceptron, a simple single layer perceptron, cannot separate a non-linear problem space. Any of you hearing music? I seem to hear music. How come? Actually, it's from this from my headphones. Someone maybe any of you turn on your. No, no, you guys don't hear. Only me. Funny, hearing music. Oh, I think I know why. My video is still on. Now should off. Now it's off. My video, just now the video on the smart agriculture was still playing the background. I did not turn it off. Sorry about that. So back to here. Perceptron as a linear separator. So linear here, you're looking at yes or no, red or blue. So here, your linear separator or binary classification can be viewed as a task for separating the classes in your feature space. Right? So imagine you're able to extract the features, say apples and oranges, into just the color, and maybe what else can I select? The shape. The shape is different, right? Apples and oranges are different shapes, so we have two. Here maybe it's a shape, right? And here maybe it's your color. So if I extract that, I can then maybe collect, look at the color of apples and look at the color of oranges, and then look at the shape of apples and look at the shape of oranges, and then this will be can be drawn on this map, on this figure here, on this graph here, right? So they can see they're well separated, especially if the data is can be separated linearly, right? So here, if that's the case, if that is true, I can then draw a line to linearly separate between these two classes. This is basically a very good example of your binary classification problem. Now, once I've drawn this line here, what else can I? What else do I know? What else can I find out? I can see that if this is my line here, right? Shown here is I can see this is a standard linear what do you call it, a line. Now here, if this is 0, so this will be more than 0, and this any points here below this line will be less than 0. So basically, you can then check out the function for you to do this binary classification will be to find what's the sign, right, of the points that you have, the new point that you have, right, after you train your network, you train your system. You not call train your perceptron, right? Train your perceptron, you can see that you just need to find out the output of your, once you train it, and any new point coming in. We have one new point here, I've shown in my cursor here. Now, with this point here, what is the sign based on this equation? If you after you calculate this one, if the sign is less than 0, then it belongs to this group of blue particles. And so same thing applies here. If I have another new point here, what is the, after calculating the location, right, of this point here, what is it more than 0 or less than, or is it more than 0? It's more than 0, then it belongs to this class of red particles. So basically, how do you choose the perfect, a good hyperplane? So in the support vector machine, you actually you can only use it if it's linearly separable, like in this case. So the support vector machine idea is to, this is important, to maximize the distance between the hyperplane and the closest sample point. Maximize so that is the foundation, that is the main idea, right? interesting idea, right? And also novel, something very new. No one else thought of it except the inventor of support vector machines. This idea is you need to maximize the distance between your hyperplane, right? This is your lead separating line, right? So in 2 dimensions a line, 3 dimensions is a plane, and more than 3 dimensions will be what we call hyperplane. So in the case of the hyperplane, the idea is you try to maximize the distance of not any point, only the closest point to this hyperplane. You try to maximize it for both classes, right? Of the closest sample point. So you need to first of all find out where your separator, right? Your separating hyperplane will sit, and from there, what are your nearest points to that separating hyperplane, right? So now in the first example here, what do you see? You see that if I draw my hyperplane, the green line here, as such, the closest point to this hyperplane will be this one, and this one. Maybe this one also can be said to be close to this line. But let's take this example first. What do you see? Yes, this hyperplane. If we say the hyperplane sits here, now this hyperplane will satisfy the first part. Okay, so I can satisfy both parts. It's actually quite large, and actually this is the closest sample. This is a closest point object or sample point to my hyperplane. But how about the other one, the other side, the other group, which is the green particles or green circles here? Yes, this is my nearest sample point to my hyperplane, but the distance is actually quite small. So I am not, can I increase this distance? So you can see that I can increase this by maybe moving this line. So that you can see that this then results in an optimization problem. So actually, how do I move this line so that at the end of the day, both parties are satisfied? So this is the optimum point, find the optimum line, right? I think this will be explained further in the next few slides. Now, you say that just now, the distance is, the line was too close to here, so I move it further away. So I'm trying to maximize this, right? So I increase this, maximize the distance here from the green point to my hyperplane. Now, once you do that, this fellow will suffer. What you are actually encroaching, you're actually eating into his distance here. So there's also no good. You make this point happy, but you make this point unhappy because the distance now is too close. So in the optimal hyperplane, that means in the best hyperplane, right? The distance of say for example, below this line is, let's call this negative. The distance to the closest negative point will be equals to the distance to the closest positive point. It's actually quite intuitive. You don't need to really, study whatever to actually tell you that. It makes sense. You can see it's common sense. The best point will be then this distance will be this is an equal distance for both sides. But you only take for that one point. You don't take for all the points. This point you don't consider. You only took at this point. So in a way, what does it mean? I think later on we see that actually it is what do you call it? It is cut down your calculation. I don't need to calculate the distance for every single point. Only the nearest points to my hyperplane. So first thing is the best line you can draw, the best hyperplane you can draw, the best separating hyperplane you can draw is something that is of equal distance to both the negative points and the positive points. So moving along, the support vector machine's goal is to maximize the margin, which is basically twice the distance d between the separating hyperplane in green here and the closest sample. Now here you can see this one actually I was right. So this point and this point are actually located at the same place, so that not same place, it's wrong for me to say that. Located at the place whereby the distance are the same. So this will be your 3 closest points to the separating hyperplane, and this is known as your margin. So margin equals to 2d. D is the distance of your closest point in the negative region to the hyperplane, and the closest point of the positive points to your separating region, separating hyperplane. Any questions? Any comments so far? Can follow, right? Okay. Now, why it is the best? Why it is the best to have a margin which is twice the distance d between the separating hyperplane and the closest sample? Why it is robust to outliners, as we saw, and thus give you a strong generalization ability. You're able to generalize very well, because later on you come to that, explain further. Now, furthermore, it proved itself to have a better performance on test data in both practice and theory. So scientists have studied this and find that if you have such a margin, which is 2d, and this separating hyperplane lies right in between the closest positive points and also the closest negative points. This will give you the best performance, both in practice and in theory. Theory means that you actually calculate it mathematically. Now, the support vectors. Now, so far we talk about support vector machines. So far we not explained why do we choose that word? Why do we choose this name of support vector machines? Now, support vectors are defined as the samples closest to the separating hyperplane. So these are your support vectors. Once you identify them to be closest to your separating hyperplane. So you can see here we have 3 support vectors here, here, and here. So these are your 3 support vectors, and this is a margin, and this is the distance of each support vector to the separating hyperplane. We will see later that the optimal hyperplane is completely defined by the support vector. So once you're able to identify the support vectors, then your optimal hyperplane is completely defined by these support vectors. It means that they actually will, you cannot run away, you cannot change the support vectors too much, because this is once you identify the support vectors, this will be the best support separating hyperplane that you can have. Now here, we have these 2 sets of data in the feature space, shown here in the 2-dimensional space. Squares, black squares, and green circles. Now, which of the linear separator? So will show you a few linear separator. Right here, like this, right? It still makes sense, right? It's a line. I can separate the 2 classes, the 2 objects, circles and squares, or can have a line here. And which one is the best, right? So if you have it here, then I will say that it's this point, and this point are your support vectors. But if you have it here, then it will be this point and this point will be my support vectors. Right. So the best will be this one, right? You'll see later on. Right. Now, so now let's go a little bit into a different concept, which is we need to find, because you see here, this is a convex hull. So we try to find the, if you have 2 groups of data here, circles and squares, we want to find the convex hull, and then from there, find the closest point in the convex hull to your separating hyperplane. So what is a convex hull? A convex hull of a set here of points is the smallest convex set and contain all the points in S. So this is my convex hull for green circles, and this is my convex hull for my black squares. Now then from there, of course, this convex hull will circle, will also cover all of the members in that particular set. And then of course, once you've done that, you can then find the identify which would be your support vectors as you see later on. Right. So if this is your convex house, then from there I will identify the what I call the closest point to the the distance between the two convex house. Right, and then this is actually now we're going to see how we can actually identify where your separating hyperplane will sit. Right, so once you have this, then you find that this is the closest, the 2 points which is closest to the point which is closest to the neighbor to the other convex hull. So in this case it's C, and then in this case it will be D, which is closest the point here in this convex hull, closest to the neighboring convex hull, which is here. Okay, you able to draw a line here, right? Once you draw a line here, then you bisect that line here and to determine your separating hyperplane. That's how we actually do it. Of course, you have to work it out in the algorithm. And then once you've done that, you then actually say here these 3 points will probably qualify as the support vectors, which is your closest point to your separating hyperplane. This one and this one. So that's why we draw this out. Right? You can see these are my three closest points, sample points to my separating hyperplane, and as a result, they are known as your support vectors. So let's continue to look at now another set of data as shown here. Suppose we choose a hyperplane seen below here that is close to some sample xi, in this case, the red points here. Now, suppose you have a new point x bar. Okay, this one actually trying to explain why it needs to be the separating hyperplane needs to be the distance of the separating hyperplane to your data points should be as far as possible. Should be have a largest distance possible. You explain why. So in this case, it is not maximum. It is quite close, very close to this point here. Now suppose you have a new point x bar. So for some reason, your support vector machine have identified that this is the best separating hyperplane I can have. Over here, shown in the green line here. Now, suppose you have a new point here. Now, after training the system, right now I have a new point. I want to see this piece of data. Is it apple or is it orange? So this one we do not know. So based on this, so this point, we know that this point is actually belongs to this class, the red class, which is actually should be below what we call -1. Right? Should be actually, remember I said this before. If the point is actually below this line, so all these points belong to the -1 class, right? Because they are below the hyperplane, separating hyperplane. So they should belong to that. And we know that in fact, the ground truth is that this new point should also be a member of this -1 class, right? And this one, because it's also close to xi, this other point, right? The train point, the point that the system learns. Now, using our classification function based on this separating hyperplane, this point would be incorrectly classified or misclassified to belong to the +1 class of the stars here, because this one lies above the separating hyperplane line, separating hyperplane, right? So this one actually, because of this, right? Because of this, it is concluded that if you were to identify, if you were to decide that this is the separating hyperplane, this system will then give you poor generalization. It's not able to generalize correctly. It give you wrong results and say that this point belongs to the +1 class of the data. So basically, it's giving you poor performance on unseen data, as shown here. So this is actually, again, we are trying to say that the hyperplane should be as far as possible from any of the sample points. So that's why we're trying to explain why you should keep it, put it as far as possible from all the support vectors or the nearest points from your convex house. This way, because if it's as far as possible, right? Going back to our earlier example, this way, new data, x prime, that is close to the old samples will then be classified correctly. So now if you were to recalculate our separating hyperplane, move it up, as shown here, you find that as a result, now my x prime will then be classified as belong to the class of -1, this group, right? And again, you can see visually, this one makes sense because it should belong to this group and not to this group. Because you see the distance of this point to all these points here is closer compared to any of these points here. So it makes sense. This is similar to these points here. So as a result, this is actually said to be, we conclude that as a result of this hyperplane, right, it gives you good generalization. It gives you good generalization because of the fact that it is pushed now as far as possible, right, further away from this class here. And it is equal distance between the support vectors. So the support vector idea, support vector machine idea, is to maximize the distance between the hyperplane and the closest sample point, as we pointed out earlier on, 2 slides ago. So now this is no good, right? Because it's no good. And then another example, if you push it further up, also no good, right? Because this is maximized, but this is it will give you poor generalization on data that is close to any of these points here. So of course, the best one will be the distance of the closest negative point equals to the distance of your closest positive point. Now, so further on, we will now talk about the what do you mean by, so from that definition, we now come to a new definition, which is the classification margin. Your classification margin, right? This is your margin, will be equals to, this is the distance from the example point to the separator. So we are looking at the classification margin, which is your distance d here. Now, so this is the actual distance, the data closest. First of all, we know that this distance closest to hyperplane are known as your support vector. So if you ask which are the support vectors, or rather ask to identify which are the support vectors in your in this data, you should know that this actually will be this point here, this point here, and this point. So we have 3 points here. So it again depends on the data set, and also depends on where you draw your separating hyperplane. So therefore, the margin P now of the separator is the width of the separation between the classes. So this is a 2D, right? So this is you can see this is a distance between the two classes, which is 2. So this is the distance D from the closest, or rather support vector, closest sample point to the margin. The same applies here. So these two, as you said before, this will be same distance, same answer. So this is your margin now. This is the margin, which is 2D. Maximum margin classification. So ultimately, we want to maximize the margin of classification. So as I said before, if you were able to maximize the margin, right? It's good according to intuition as well as theory. It implies that only support vectors are important, right? So as I said before, this is one of the strong points of your support vector machines. We only look at support vectors; the rest are not important. So as a result, you do not need to spend more time calculating the distances of the other points. So you need, in this case, you only take 3 points to calculate, to find your best support vector. other training examples can be ignored. So this is part of the statistical learning theory. Right? So now misclassification error as shown here. We go back here. This is actually misclassified. So this is your misclassification because of your incorrect separating hyperplane. Right. So your misclassification error and the function complexity bound. This is your generation of error. Now, maximizing margins minimizes complexity. If you were to maximize your margin, you're able to minimize your complexity of the problem itself. And it also eliminate, or it will, you look at it, it will eliminate, basically not eliminate, basically it will minimize your overfitting. I think later on we'll talk about this overfitting. It means that it's able to learn very well one class, but not the other class. That's what's meant by overfitting. So as I said before, the solution depends only on the support vectors, not the number of attributes. So even I can use these support vector machines efficiently, even for me to classify, right? To separate 1 million points, because I will look at the 3 points, for example, 3 or 4 points, which are my support vectors. That's one of this. I said this is one of the beauty, one of the advantages of your support vector machines. Now we talk a little bit about the size of your margin, right? We look at the skinny margin. It's more flexible and therefore more complex. The skinny margin is more flexible, plus it's more complex. You can see here, I can have it here, I can have it here. Now, fat margin is less complex. So this is your fat margin. So I can only have one. I don't need to have just now here, right? For skinny margin, I can have 2 choices. So it actually increases the complexity of finding the margin, the separating hyperplane between the 2 classes here. Now, hyperplanes, again, let us visit what are hyperplanes. In the 2-dimensional space, hyperplane in the 2-dimensional space is a line. Now, in a hyperplane in 3 dimension is a 3-dimensional plane itself, right? This is a plane, not a hyperplane, just a plane, separating the 2 classes here. Okay, now we will maybe stop for a short while before we go into to calculate, show you how to calculate and find the what we call it, the separating hyperplane for this simple set of data. Now, before we stop here, to take a short break, before we come back, are there any questions or comments? Okay, if not, we take a 5-minute break and then come back. We will then go on to how to see how we can calculate the identify the what we call it, the hyperplane, also calculate all the various things, the margin as well as the distance between your support vectors to the hyperplane itself. Okay, let's take a short 5-minute break. Thank you. Okay, we will start very soon. All right, and we'll continue recording. Okay, let us continue. Now, in this example, you can see here I have 4 blue circles and I have 4 red squares, right? So basically, we have to. First step is we are going through the steps of how to actually calculate the separating hyperplane. So first of all, identify 3 of the support vectors. In how do you identify them? Ensure there are sufficient numbers from each class. So you need to, if you were to identify the support vectors, you need to identify 3 of them. Later on, we will see why we need 3 and not any number. Of course, you get more than them. More than them is okay. More than 3 is okay. But less than 3 would be a problem. That means that either 2 or 1. 1 is outright. You cannot have 1 vector. And then for you to fix your line, fix your hyperplane. So then you form the equations of for each of these 3 support vectors. So in this case, I can see here, this will be my what I call it, the convex hull for the blue circles for one class, and then my convex hull for the other class. I draw this up. This is my convex hull for the one class, which is my red squares, and then the other one is actually my convex hull for my the other class, which is my blue circles. So from here, this will be my, this is my, I need to draw it up. Maybe I don't need to. So I need to draw it up. Maybe I'll just put this sort of cap on standby just in case you need to draw this up. So we can have it here. Now if I use my pen, so this is my, now where are my support vectors to be? Here again. Control options, in color, is green here. Okay, this will be my change the thing, my screen is seen. Okay, there you go. This is actually over here. This is my one of the support vectors, 2, and then 3 of them. So satisfy my 3 support vectors. So first of all, you need to identify where the region is, where your hyperplane will probably sit. So then you form the equation for each of these 3 support vectors. So how do you do it? Now, first of all, let's say that this is my, let's call this this point here, this support vector S1, this support vector S2, and this support vector S3. Let's see here, what is the actual coordinates of this support vector S1? So you can see here, this is actually X is 2, and so we have your 2, 1, S2 will be 2 minus 1, and finally the third support vector will be 4, 0. So that is the first step. Next step is you need to add a bias for each of these 3 points. Right? That is the step involved to actually calculate the distance and so the separation between the two classes of support vectors. So once you add the bias now the bias is that normally now why do we use a bias of 1? Why not any other number? You can also use any other number, but it's of course easier to calculate on 1. So it's just for simplicity. We put a bias of 1 rather than any other number, right? We cannot put 0, right? 0 means it's as good as not putting a bias there. So we put a bias of 1. So we from here, let's make my pen. From here, it becomes here. So this is your bias, and your bias. So that's how we actually modify your three vectors, the three support vectors to these three to these new values as shown here. So number 3 now, based on these three new equations of your support vectors, which has the bias, right? You then form the equations. Now, you multiply. Basically, you put basically you can see here. I'm actually looking at the basically linear equation for, first of all, this will be tilde S1, right? So this is the first one. I can draw it here. Alpha 1 S1, and you're multiplied by S1 again. So basically, you look at all the possible combinations. And finally, you have the X3 as well. So this one is space. I need to change this. Maybe I'll do it here. Right, this one here. I draw it here, right? Alpha 1 S1 tilde S1. You basically look at all the possible combinations. S1, S2 plus alpha 3, S1, S3 equals to, now, notice here, this is actually -1, -1, and +1. Why is that so? Oh, sorry. Yeah. Now, if my line is somewhere here, where's my cursor? If my line is somewhere here, for example, so this one to the left will be, let's call it class -1. I call it class +1. So it's up to you to arbitrarily set, right? So you just set it. You can also do it +1 here, and make sure this point will be -1. So it's as simple as that, right? Right. That's why notice here we call it -1. So this one belongs to what called the point which is below your separating hyperplane, and this other one will be above your separating hyperplane. That's all. So this is -1, and do the same thing. The second one, usually the same constant. This will be 1. Oh, actually the other way around. Let's try to see the other way around. This will be S2, S1. Actually, it's the same thing, right? But remember, just follow the convention here. So this will be 2, 1, 3, 1. The next one will be 1, 2, alpha 2, S2. Okay, never mind. Do it this way. 4, alpha 3, S3, S2. Tilde. Now, this will be S2, S2. Now, if I want to highlight this, I show you what are the differences. This one will change. Okay. Okay. So this will be, where's my pen? So I have my 1, 2, 3, sorry. Okay. 2 as 2 as 3 as 3, right? And then you have your here, so you have your where is it? -1. And find the last one here. This is this one here. So will be alpha 1 again, your 1, 2, 3, right? In this case, S1 plus alpha 2 S2 plus alpha 3 to the S3 multiplied by, this is now, third one can see here, 1, 2, this will be third one. So basically, you try to get all the combinations. Now, this one is actually because it's actually, we say that this is above your, or to the right of your separating hyperplane. So this will be your last one. That's how you get the 3. So basically, you have to take care of, make sure that you know where the points are, right? Where the points are, and which one is actually, we say this one that will be, this one will be -1 class, and this is your +1 class. That's how it's reflected here, 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 here. Now, once you got that, you then multiply out the 2 vectors here, and then of course you need to. So there will be a bit of calculation involved. So after that, you simplify, you get this. Okay, now we have 3 nice, beautiful equations here. Change it back to red color. Right, you can have it here. Maybe I'll use my pointer. Okay, so we have here one of them. So this is my first here. I simplify this, I get this, rearrange that. Right, so you have to make sure you have some, I think, what called rough paper for you to do your calculations. So that's that. You can see I have 3 linear equations here, and of course I can then solve them to calculate, to find out what's my alpha 1, alpha 2, and alpha 3. These are alpha 1, alpha 2 are my constants. Now, if after your calculation you find that alpha 1 will be -3.25, alpha 2 will be also -3.25, but alpha 3 is actually 3.5. Now substitute back. So now your what you find your alpha 1, alpha 2, the 3 constants, but your hyperplane, the hyperplane we're trying to find, hyperplane here will be is one class to the next class is defined by the set of weights, which is your alpha 1 times your point x1, point x2, and the point tilde x3 over here. Right, so this is your basically your general equation for your separating hyperplane. So this one is actually something you must also remember, that the separating hyperplane for this 2-dimensional example, right? Of course, if you go for n-dimensional, it will be more complicated than this. So let's keep it to the simple case of the 2-dimensional support vectors for this problem. It's only 2 dimensions of two set of features in my problem space. So alpha 1 times the first point, alpha 2 times the second point, and alpha 3 on the first point. So Again, if you now substitute back alpha 1, alpha 2, alpha 3 into this equation, you get you can then find out what is your W. So if you were to put this back here, and then you find that to solve it will give you W equals to this. Now, this W is needed for you to define your define your separating hyperplane, which is a linear. This is the actual equation that defines the linear hyperplane. So you can imagine if you were to try this on the other the hyperplanes, right? Non-linear hyperplanes, it will be very tricky. But in this case, we always say that the support vector machine is that the beauty of it is that it always looks at the linearly separable cases. Now, if your data is not linearly separable in the lower dimension, you convert them to a higher dimension, making sure that when you convert them to or transform them to the higher dimension, they become linear. So you always use this equation to solve your problems in the support vector machines. Now, the actual equation that defines now your separating hyperplane will be y equals to wx plus b. So now you have your w defined, right? And x are the values to define hyperplane. Hence, for y equals to 0 means that you have y equals 0, right? So your x equals to 3. It's a straight line at what x equals to 3, right? So for that, so you have your x1 minus 3 equals to 0. Therefore, your x equals to 3. So it's a okay. I think we'll show you on the next slide. You find that basically your hyperplane will be looks like this. So that's why you define now your separating hyperplane. And why is this optimal? Because you find that if it's x equals separating hyperplane is x equals to 3, you find that the distance of the support vectors from the -1 class is 1, and the separating distance, the distance to the support vector of the +1 class, that is your rate squares, will also be 1. Therefore, this is your optimal hyperplane. Now, how do you calculate the distance of the separator to the of the support vectors to the separating hyperplane? Now, this is I'm showing to you how we can actually derive this. This is going back to the mathematics to actually trigonometry to actually find out the distance of any point to your line here. So this is actually to show you. Of course, you do not need to define it from scratch. If you can, of course, remember how we actually use the equation, I shall show later on. So for now, for the general case of an orthogonal distance, so we are trying to find the orthogonal distance, 90 degrees distance from any point P to your line DE here. So this one will intersect at the point here, Q. Now this one will be your general equation for your separating hyperplane. Right? So in this case, A, B, and C are the constants. So I'm just showing to you. So of course, this one, I think maybe some of you may actually already know how you calculate your perpendicular distance, any point to the line DE. Right? So we construct a parallel line from P. This line is parallel to your line DE. Now we do a trick to make things easier, so that for ourselves, we construct a line parallel to DE. Right? Well, first of all, call it FG. Then we construct another line parallel to PQ. Now this is the actual point that intersects to my point Q. But I also want to draw another one which actually parallel to this, right? So this is let's say it's RS, and this one of course intersects at 0, 0, right? So this is a parallel line to your PQ passing to the origin, and I extend this right up to the origin. So therefore, if you can do that, then the distance of your orthogonal distance for RS, since it's parallel to PQ, you can then say that orthogonal distance from PQ is the same as your distance for RS, which is given as such. So once you're able to form your general equation for your line dq, sorry, dE, which is this line here. So make sure your what do you call your equation for your separating hyperplane must be in this form. Now then from there you can then pick up the values for A, B, and C. And once you do that, you can just apply to this equation here, right? So the distance of RS or PQ will be the magnitude of A times X. So AX will, X and Y will be your, in this case, M and N, right? So actually it will be the distance here. So the ABC will be the constants for your line DE. So this is your actual equation for you to use if you're asked to calculate the distance from your orthogonal distance from your support vectors to the separating hyperplane. So in this case, it's a line for two-dimensional case. So this actually is the additional information how we actually arrive at this equation. So I actually simplify it without going to the details, and then you find that if you're not convinced, of course you can go back and look at this derivation to actually come up with the actual example here, the actual answer here, which is right here. So this is all the derivation, how you arrive at that. So this is all basically the mathematics behind that over here. So this is actually taken from the internet. I think that this is a standard perpendicular distance from a point to a line, right, to a straight line in this case. So of course, you do not have to derive this, but of course, if you could, of course, if you can derive this. Otherwise, you have to remember how to use this equation here. Use this. Now let's go to our example here. Let's say now I want to find the distance of the a point, the perpendicular distance or orthogonal distance from point 5, 6 to this line here. Now this line, I will first of all have to find the general equation for this line in this form. So you have to make sure the line, this separating hyperplane, will be arranged into this form. And see here is minus 2x plus 3y plus 4 equals to 0. Or if you like, you can also, you can also rearrange it into this form. Maybe this one will be simpler for you to remember. So this line here will be 3y equals to 2x plus 4, right? So your y equals to 2 over 3x plus 4 over 3. Well, of course, this is your one way of describing this line. But of course, you need to make sure you need to transform this back into this form, right? So that here will be, so A equals to minus 2, B equals to 3, and your C equals to 4. Remember, the distance will then be, I don't need to draw it here. Okay, let's see here. So here, if you remember, so we have this, right? So we can then, right? So you see here, minus 2 is here, right? This is your A, this is your B, this is your C. Then your point here will be, just erase this. Clear the space here. Okay, so you can see here, right? Your M and N equals to 5, N equals to 6. So you can actually just put it in and then you get the answer. So this distance will be 3.328. So again, you need to emphasize here again that the actual your hyperplane, the separating hyperplane must be written in this form. Let's go back to our example right here. Right here, so we know that this hyperplane that we actually define here is a straight line. Actually, is x equals to 3. So basically, it is if you rearrange it, so basically it's 0 y plus 1x minus 3, right? equals to this form. So this will be x minus 3 equals to 0. So basically your y equals your, what you call your no, it's like b, isn't it? B, right? So have your standard form is ax plus by plus c equals to 0. Therefore, in this case, your a equals to 1, your b equals to 0, and finally your c equals to minus 3. That's why you actually remove here and then you put it inside here. B is 0, A is 1, and C is minus 3. So you get your distance of 1. So ds1. So the distance of this point, this support vector to your separate hyperplane is 1. And so is your distance of your point support vector S3 to this separating hyperplane is also 1, as shown here. Provided you remember the equation here, right? This is equals to the magnitude of A m plus bn plus c, right? Over square root of a squared plus b squared. Any questions? I know it's a bit quite difficult. Step 6 of calculation of how. Wait. There was a question from Kai Liang. Let me check. Step 6. So let's go back. Oh, sorry. Oh, here. Is this one? Kai Liang? How do I derive x 1 minus 3 equals to 0? Oh, okay. I think let's skip a few steps here. If you go back here, right? So we actually found out that the, what do you call it? The W, the weight is equals to, as shown here. So this will be my, that's my pen. Right here. So this will be my AX, B, Y, and C. Right, as shown here. So this is my separate, in this case, I can see my actually y equals to, right, you see x plus 0 minus 3 equals to 0. This is my standard equation. This is ax plus by plus c equals to 0. Therefore, your x equals to 3. Is that clear? Okay. Any other question? I know it's a bit, this one's a bit, can see actually support vector machines actually can be quite mathematical, right? And good news is that we will not go into the non-linear, what do you call it? Actually, we have not even touched on the kernels. We're only looking at once you're able to transform your data into this form, whereby the data can now be linearly separated. The data now can be linearly separated. So initially, I think I'll show in the next few slides, maybe at the end there, I'll show you what I mean by that. So the so-called, if you like, beauty, the advantage of your the strength, the strength of your support vector machines is that it is able to, once you're able to get your data transformed into high dimension into this linear form, whereby now it's linearly separable, then I can then apply it by using the, first of all, find the support vectors nearest point to your separating hyperplane, and then from there draw the line and separate up, and then from there you go transform back to your initial data in the lower dimension. I think I'll show this in the later slides. Okay, good. Okay, so first of all, okay, where am I? Okay, important. Make sure the hyperplane must be written in this form. And then we are showing how to actually calculate the distance from the what I call it, the support vectors to your separating hyperplane. And then now question is how do you decide the support vectors and your separating hyperplane? So of course, if you look at the data here, you try to draw the convex hull over your points. Now this is under your training phase. That means that the data now is given as such, right? So from the data given here, you know that this one belongs to. So during the training, you know which data points belong to which class. So as shown here, I know that these 4 points belong to class -1, and these 4 points here belong to class +1. Right? So can I do it this way? Right? Is this a better hyperplane? No, because this distance here is not optimal. It's too near, right? No, actually, it's right. Actually, no, sorry. Let me rephrase that. I can also have a hyperplane like this, right? Now let's touch about it. People can see here, there's no one way of calculating or no one way of determining your hyperplane, right? Now this one, the distance here is still, what do you call it? Oh, okay. So let me explain why. Let me explain this in a bit different way. Let me try to explain it in a different way. Okay. Now, just now, for the past half an hour, we're looking at this hyperplane. Now, what do you have here? Your S1, S2, and then your S3. That means that for my class -1, I have S1, S2, and my class +1, I have my S3. This is my one. This is my. I selected this, or rather, I think my hyperplane is here. So I then define these two as my support vectors, and then this my support vector is shown here. Now, in this second example, what I've done, I have my let's call this S4 now. Now, S4 is still a support vector because it's actually closest to the hyperplane. But now I have my S1 -1, my class -1. I only have 1 point. Now my class +1. Now I have 2 points. Now both cases are still all right, acceptable, because it still fulfills the requirement that the support vectors must be closest to hyperplane. So what does it mean? It means that for you to select your support vectors, there's no one answer, at least shown here in this case, right? So it's an optimization problem. For you to optimize, to find which is, I can also do this way. I think this one is okay. This one is okay. I think this one is a little bit same. This one is actually same thing, isn't it? I have my let's call it S5. So the third case will be, I still have my -1, which is my the support vector S1. And then the other one is actually +1, my support vector S3 and my S5. All 3 cases here, let's call this P support vector, they call V1, V2, V3 are still all right, acceptable. Now, let's now move on to look at some of the problems associated with support vector machines. What are the problems associated with that? Now, what if the decision function is not linear? So far, we talked about in the previous example, right? It is linear, linearly separable. I can draw a line. I can separate between the 2 classes. My red circles, my blue circles, and my red squares. How about here? How do I separate my green circles and my red circles? So the decision function, I can still do it, but in this case, my so-called separating hyperplane is no longer a straight line, or it is also not a plane. It is a circle, non-linear. That's what it meant by basically non-linear. So what do I do? So can I say that support vector machines cannot work, right? So that is one of the things we actually talk about. Overcome such things, what we do, we transform this into a new dimension, or maybe higher dimension, whereby the separating hyperplane is now linear, as shown in the next few slides. Another example, right? So you can see it here. If we were to visualize this, of course, this is during training. We know that the blue circles belong to one class, and my red circles belong to the other class. And in this example here, I have 800 points. Right? So can I apply my support vector machines method to separate these two classes? Yes, you can, but you need to do a little trick through the use of your kernels. Now, for such non-linear data, right? Non-linear data, the support vector machines uses the kernel trick. If you read the literature, you read the papers or books on these support vector machines, they always talk about this kernel trick. Now, what is this kernel trick? Basically, it uses a kernel function to map the non-linear data to higher dimensions so that it becomes linear, and then therefore able to find the decision boundary there. Right? So this is non-linear. Can I use some sort of a transformation? This is what you call kernel trick. Use a kernel to map this, transform this into a higher dimension, right? So that now it becomes linear as a result. So the kernel function is always used by the support vector machines, whether it is linear or non-linear. So you use the kernel function, even though the data itself is linear. So then the kernel will be simpler compared to the non-linear case, whereby the kernel would then be more complicated or more complex. So this main function comes into play when the data is now inseparable in this current form. If the data in the current form, like here, cannot be easily separated, right? Not linearly separable. So the kernel will be very useful to actually once you transform them, the support vector machines will then be able to classify for you. Here, the kernel function adds dimension to the problem for classification. So we can also argue or say that as a result of this kernel function, of the appropriate kernel function, I'm now able to use my support vector machines to separate the two classes of data that we have in the new dimension. Okay, so this is actually an example of how the kernel trick, right, is employed, and how actually as a result you can then see that actually support vectors can then be used, because now then the data in the new dimension is linearly separable, right? So with an appropriate kernel, we transform the initial space to a new space. So what you see here, so the initial data is in two dimensions, x and y. Now with the appropriate kernel, right, whatever that is, you can it's like you select the best kernel. Again, there's no one best kernel, so you have to play with it to find the best kernel. You transform that into this three-dimensional. Once you transform the three-dimension, right, you can see that now I can just draw a plane, right, a plane in this three-dimensional space to separate my red dots from my blue dots here. Another one, similar thing, right? Again, you can see here 2 dimension into 3 dimension. Basically transform it into the new space that the two classes can now be linearly separable, and this is my decision, what I call separating hyperplane or decision surface. So I can then easily, so what you see, the trick is actually, if you cannot find the appropriate kernel, if you cannot identify, get the transformation done correctly, this will be a difficult task for the support vector machine to actually classify, to separate. So here, another one, right? So this one is a different example. Instead of this one actually is still mapped it to a new dimension, but it's still 2-dimensional space. But this one actually transform the points, move them Right? This point here is moved to this space here. This one is moved over here, and as a result, I can then still define the separating hyperplane or a line, right, to separate the two classes here. But this one actually does it differently, right? And move, in a way, it's still the same because I still move them. I still move the points, right, to a new dimension. So I move the points to a new dimension in a new space, new feature space, right? This is your initial feature space 2, initial feature space 1. But by using another kernel trick, appropriate kernel, I'm able to move these points here so that now I can just draw a straight line, which is my separating hyperplane. And thereby I can then use my support vector machines to separate the two classes. Now, as I mentioned just now, we touch a little bit about overfitting or overtraining. What does it mean? So the well-known problem with machine learning methods is overtraining. You actually train it too well in a way. Right? This means that we have learned the training data very well. We give you 1,000 or 1 million apples to look at, right? And also oranges. But because you are very well trained in the training data, you cannot classify unseen examples correctly, right? So actually, your vision is very narrow. Example here, a botanist really knows about trees. Every time she sees a new tree, she claims it's a tree. It's not a tree, right? So because you are actually well trained in looking at trees. So when you have a new data which you have not seen before, you then claim that this is not a tree, although it's still a tree, right? So this is what you mean by overtraining, overfitting. So it's one of the problems that not only in support vector machine, but in all other intelligent methods, especially your neural networks as well. If you train it, and there's also, I think some of you have not, maybe have seen it, maybe not now, but later on you might see it. Something also called class imbalance. Means that you train it very well. You have 1,000 pieces of data for class 1, but for class 2 you only have 10 pieces. So this can also lead to problems of class imbalance. Your machine learning method, right, can only sees a lot of class 1. It doesn't see class 2, for example, right? So then, of course, there's overtraining, overfitting. There's also another one on the other side, which is underfitting and overfitting. This is actually overfitting over here. So what do you mean by underfitting? Underfitting is basically this is your basically your, I think, your data here, right? Blue one is a model. The actual true function for you to classify the two classes actually is a green line, and the dots here are your samples. So in this case, underfitting, you simplify methods. You just draw a line over here. Now, actually, what your machine learning method should produce for you is closely follow the green line. It's ideal. Ideal. Now, overfitting is you only learn certain points, right? And then your model here, I see, it takes every point as belonging to your class, so there's nothing left, right? So as I said just now, it becomes a new point. You say that point is not a tree because you are overfitting. It tracks every single point, right? And so your machine learning method will collect what you have now. When a new point comes in, what happens? It will not, especially if it doesn't sit on this line, it will then be classified as not a tree. That is your overfitting. So I'm trying here to explain to you what is your underfitting and what is overfitting. Of course, the ideal one will be actual fitting, optimal. That this is a line. So any point coming in here will be classified as belonging to this class or this class. But here actually is underfitting. So we can see here, this is actually will be belonging to one class, and this is belonging to the other class. This is actually incorrect. So this actual one line should be here. This is your decision boundary. Again, it is non-linear. So let me see it here. Underfitting, right? And then especially for too simple, right? You can see underfitting. So this is another example. This is another example to explain to you what is underfitting and overfitting. Overfitting, you actually force it like this. Of course, this is non-linear. So when a new point comes in, you will find that you cannot generalize, right? So this is actually this is a way you can actually what we call it trade-off to find the best point, the best decision boundary to separate the two classes. Right here, this will be the best, of course. Of course, it's trade-off. Right? You can see here, this point is actually incorrectly bundled, incorrectly grouped into the green squares. As you can see, actually it doesn't belong to that, but of course it's a trade-off. Right? So it's the best you can do. Right? But of course, it's still not perfect. You cannot get 100%. You get maybe 99% in this case. So in support vector machines, to avoid overfitting, we choose a soft margin instead of a hard one. What does it mean? It means that we let some data points to enter our margin intentionally, but we still penalize it so that our classifier do not overfit on our training sample. Overfitting, right? So that is one of the tricks you can do to actually make your support vector machines perform better. Now, some of you may actually want to use support vector machines in your FYP. So at least be aware of such issues affecting your support vector machines. To summarize, I think we come to the end of this topic here. So what is a support vector machines? So support vector machines actually is one of the advanced topics, and it's not in the book by this Michael Levinsky. So we have to look for other sources in case, especially in case you cannot understand, look for a simple material. Of course, if you choose to find information on the internet, maybe I can say 90% of them are quite all right. So you have to be cautious when you read up the information on internet related to support vector machines. So basically, the first point is that it belongs to a class of supervised learning algorithms and uses the concept of margins to classify between classes. So it's a supervised method. You need to tell it that this data point belongs to class A, and this data point belongs to class -1 or +1 for the method. So you have to be aware of that. So this is supervised. So you have to train it, right? What you've done, what you did in your assignment. So you put aside some data for it to train. So based on this data, where are my boundaries? So when you test it on the unseen data, does it still give you high accuracies? Now, how does the support vector machines basically perform, able to classify the data? It performs this with a hyperplane, right? So this is, I think, before for the past 1 hour or so. This is your separating hyperplane. Because why we use the word hyperplane? Because for beyond 3 dimensions, there's no, we do not know what to call it. So we call it more than a plane, hyperplane, like a hypermarket, supermarket. Now, this hyperplane can be a single line in the case of a 2-dimensional data, and can be a plane for 3-dimensional one. Beyond 3, we just call it hyperplane. Now, support vector machines, as the name itself, uses the concept of support vectors, which are the closest points to your hyperplane. So these are the main concepts associated with your support vector machines. It uses the calculates based on the closest points to your separating hyperplane. Strength and weaknesses. Now, the strength is that it can provide high accuracy. So I think if you do your literature review, you find that the support vector machines actually in many case studies, many experiments, many research has shown reasonably high accuracy. It has low complexity because why? You only classifies or based on the data that is actually linearly separable. Basically, just find a hyperplane, a linear hyperplane to separate the two classes. It also works quite well for non-linear data, provided you're able to find the correct kernel to push it to separate them in the higher dimension into linear data. Weaknesses. It needs more training time compared to other algorithms such as naive Bayesian. So studies have shown that it takes a long while for you to to find the optimal hyperplane. So it's not that straightforward. It's not that easy. Right? It's a long time to train it to achieve a reasonable accuracy for that particular separating hyperplane. Okay, so I think we will come to the end of this topic. So this material has adapted from this presentation on support vector machines by Motas Al-Haj, University of Haifa, and also I've also told you about the book itself on Introduction to Support Vector Machines from this book itself, and also the papers by Babnik, and also I also extracted the information, the data, the information, the PowerPoints from this tutorial and support vector machines, data mining and knowledge discovery. I think overall it's a pretty strong method. That's why we actually included it in your lectures into this paper itself. This will be more of the more of the advanced topics. And the other one, of course, is your swarm intelligence. So just to summarize that, now we conclude. What have we learned? Hopefully, what have we seen? What we learned here? We look at the history and motivation of the support vector machines. How was it? When was it discovered? Why do we propose such a method? Right? And also, we also touched a little bit about some of the mathematical foundation, among which is actually your measurement of similarity using the dot products. Then we jump straight into the support vector machines. We talk about feature space, the initial feature space. Then we talk about the new feature space, which is transformed, which were found by the appropriate kernels. And when in the new feature space, the data itself, the data points are actually linearly separable. So therefore, when they are linearly separable, you can then use the support vector machines. Actually, if we look at it closely, what else can you see here? Now, if you're able to transform appropriate kernels of your initial non-linear data into a linearly separable data in the new dimensional space, I can also use my perceptron to actually classify my data, right? So that is one of the things. So some papers have actually proposed or indicated that your support vector machine is a glorified form of your perceptron. So it's similar to your perceptron, because the trick is that if you can transform your initial linearly inseparable data in your lower dimension into higher dimension, whereby now it's linearly separable, then I can also, it's similar to I can also use back my perceptron to do that, right? But what the trick is actually how to transform from that linearly inseparable lower dimension data into that higher dimension, whereby it's now linearly separable. Because of the fact that this is basically a classifier, so we actually touch a little bit about what you mean by classification and what you mean by clustering. And of course, in the last couple of slides, we talk about the hyperplanes, and then we also show you how the kernels transform your low dimension data into high dimension. And as a result, then you can form your hyperplanes to separate the two classes, right? We also spend some time to actually look at one example, how you calculate the distance and the margin between your support vectors for a simple case of a linear simple support vector machine. Now note here, some of you may not realize this, but basically support vector machine is a binary two-class classifier. It can only work for class A, separate class A, class B. So it cannot separate more than two classes in its original form. But with the appropriate modifications, right, scientists are actually able to extend its usefulness to multi-class classification. But basically, the true form, the initial form of your SVM is actually only works well for two classes. But of course, you can modify that to work for multiple classes. Okay, so we come to the end of this topic, and also the end of this I think we have finished the complete syllabus. of your artificial intelligence, BTH 4413. Now, we still have, next week, we still have the tutorials for the various tutorial groups. And for Wednesday and Friday, we still have the lectures whereby we hope to do some revision of the various topics that we have studied for the past 30 weeks or so. Okay, if I'll stop here. Are there any questions or comments before I shut down the class? No? Okay. Then we dismiss the class. I'll see you back. Next week. Stay safe. And then, oh, by the way, there's a major just to share. Let me shut down this one first. Okay. The campus is starting to waken up. That means that I see a lot of people coming back to the campus, and also if you ever come back to the campus, you find that there's a bit of construction going on. I think they're starting to build the student center, and also I think the new car park, plus the new buildings in the football field, near the football field. So there's a bit of construction going on. So things are, I will call it, if I may call it positively, things are improving here, and students and staff are starting to come back. Okay, if nothing, I'll stop here, and I'll see you back. Have a nice weekend, and I'll see you back next week. Any questions, comments? If not, we stop here. You can go for your lunch. Okay, thank you. Bye-bye. Stay safe.
Thank you, sir.
Welcome. See you back next week. Don't forget.